So, thanks for the introduction. As you can hear, my voice is shot today. So please, if you can't hear me, please yell or wave. Can you hear me at the back? Is it okay? Okay, thanks. So, well, most of my ad slide was already in the introduction, so please check out our blog. Comes up whenever you Google for funktionale Programmierung. So this talk is going to be a little bit technical, I'm afraid. So I think most of us have probably written GUI programs at one point or another, and at least after you've written one, for the next one, you always make this big resolution, or at least I always make that big resolution that my next GUI program is going to be so much better than the last. And somehow, Falco Riemenschneider also talked about this morning, somehow when you use traditional toolkits for doing GUIs and traditional paradigms for doing GUI, your program often ends up like this. And the reason for that is that the model view controller paradigm is often described with a picture like this, where, well, you have these three things, and don't worry about what they mean, but you can easily see that, well, you can create cycles in this picture, right? And especially if your GUI is very reactive and has things running on underneath, you can have unpleasant cyclical changes where somebody clicks on a button, that button runs a handler, that handler effects a change in the model, that change in the model effects a change in the GUI, the change in the GUI again runs a handler, and you run it to cycles, and then you have to set flags that say, well, don't update just now and wait until I'm finished, things like that. And so it's fine for very simple GUIs, but for highly reactive GUIs where things are going on concurrently, it's really poor. Now, I spend a lot of time in the Scheme and Racket communities, and I spend a lot of time teaching computing to beginners. And something that I've come to appreciate here is something called a library for the Racket system called the World, or depending on when you took the course, the Universe Teach Pack. And the way this works is, well, what it does is it lets you write video games, essentially, in a purely functional manner. And the way it works is you have, well, the analog of a model in the model view controller paradigm is called a world, which is a data object that represents the current state of your video game. And what happens is then there's a function that takes the world as an input and renders a scene. So it will create the output not via a series of imperative drawing commands, but instead it will create a declarative description of the graphics that is supposed to appear on the screen, and then the World Toolkit itself takes care of actually rendering that. And so whenever a player interacts with the game, for example, by clicking on a button or by just waiting, so of course time passing is an event that's often important in a video game, another function will go and it will transform a world into the next world object. And again, that is a pure transformation. It takes a world as input, outputs a new world. It doesn't make any mutations to the original world object. And so you have this neat picture where the user interactions just create a series of worlds, and this is a completely straightforward one-way process with no cycles in there. And every time a new world gets created, a scene is rendered. So it's a really simple picture, and you'd be very surprised by the video games that our students usually write. I mean, you can easily write pretty complicated 80s style, Frogger, Space Invader, stuff like this we've done in the past, and it's easily fast enough to do that. And so. Well, what does the API look like for that? You may have been able to imagine it from the picture, but essentially a video game is described by a bunch of methods. For example, well, the method at the beginning, that one just starts the game, but then you have methods, for example, onTick. And onTick is the method that's responsible for describing what happens when time passes, 1 unit of time passes, like a second or a tenth of a second or something like that. And essentially what you do is you pass it a function that goes from world to world. So again, it's that pure function that I talked about in the previous slide. And when you want to react to an actual interaction with a user, you have a function like onKeyEvent, where you pass a function that takes a world, a key event, and then produces another world, depending on the key that was pressed. And then there's this method onRedraw, which takes a function that goes from a world to a scene. And in practice, it looks something like this. Don't worry about all the details, but you write a function like this in Scheme. Hopefully it feels slightly familiar to you Clojure programmers, where you write a function. It takes a W parameter for the input world, and as output, it produces another world object here. That's just the constructor for that particular game's world data type. And so the same thing is, for example, here's the method that handles a key, and you can see that it takes as input a world W and a representation of the key called a key, and it has a big con that looks at what key it is, if it's the up arrow or the down arrow. And again, depending on what key was pressed and depending on what the world was like previously, it will just construct another world object. And again, these are pure functions. They're not your typical rendering procedures where you say, draw a circle, draw a line, or something like that. And then finally, you define a function called that is responsible for rendering. It takes a world object as input, and then it uses various combinators to stack geometrical figures on top of each other that then yield your picture that you want to see. So it's a really, really, really nice model and suitable for beginning programmers to write pretty complicated games after, well, when we teach intro computer science after about half a year. Well, not half a year, half a semester, like 1.5 months. So we really would like, so for forever I've been wanting to bring this programming model or something like this programming model to GUI programming, and we're finally getting pretty close. But since I run a company, we really need to think about the commercial setting here and to do this in a practical context that interoperates with other software. And in particular, we noticed that for maybe for 1 or 2 years now, there's been a very pleasant convergence of GUI technologies, namely that almost every platform that you can name can render HTML5 and can run JavaScript inside, right? So of course you can run it in the browser, but of course your mobile phone will also have a JavaScript engine and will be able to display HTML5. But also JavaFX has a widget that will run HTML5. Windows apps have that. Qt has it. I think there's a widget for GTK even. I don't know how production ready that is. But it means that even if you're writing, somebody, I think Michael Sperber said that nobody writes standalone apps anymore, but even if you do, if you can somehow produce HTML5 and JavaScript to do your GUI work for you, then you can even run that on a desktop app. You don't need to run it in a browser. And so, so that gives you, first of all, that gives you that little vision we had of using a common technology for doing our graphical user interfaces, and also the potential of having things be at least partially portable between web apps and standalone apps. And so, and then we discovered another thing which is really nice, which I'm sure you've all heard of, which is the React framework published by Facebook and Instagram, I think, which gives you something that's kind of frustratingly close to the world and universe teach pack that Reacl gives you. And the nice thing about Reacl, well, it's a JavaScript framework, but you can program it fairly straightforwardly in ClojureScript. And since we also have some Clojure projects in our company, it seemed like it would be really nice to use a language that's at least pretty similar between sort of the core code and the GUI code. So here's a little snippet of React that you will taken from the official React tutorial, I think, translated into ClojureScript. So the way React works is, well, you create a class for what's called a component. And a component is going to render just a subtree of your DOM eventually. And each component must have a render method, and that render method will describe how to make some DOM, some piece of the DOM anyway, from application state. And so you can see, well, what you want to look at is the code that starts here. So there's a function called div, corresponds to HTML div elements, h2 span. So these are all very familiar. And but you can see that these functions are indeed pure, or at least they look as though they're pure, and this part is pure, in that these construct a tree of HTML elements that corresponds to the actual DOM. And so this render method is, well, if you look at it and squint at it just right, is nothing but a function from the world, from the application state of your program, to a scene, right? To a piece of the DOM that you want to be rendered in your browser. And so it's something that already looks as though it might be able to realize the original promise and idea of the Reacl teach packs. So now I want to talk a little bit about the details of that. One thing that's important that's in the rest of this talk is that each component, as it gets instantiated, so a component gets created from a class, as it gets instantiated, it receives as arguments, if you will, an object called the props. Right? And these props you can extract from this here. Well, never mind where it comes from, but and the props you can use to pass information from one component to the one underneath it. So in this case, this particular component class is responsible for displaying a comment in some simple, I don't know, blog comment application. And so what it does is it receives a props object, and in that props object, you will have an author and a text field, which reminds me that I should probably just show you that application. Oops. So of course this worked, right? Here it is, right? So here's a bunch of comments, and down here there's two text fields. You know, it says, you know, Fritz says, great, something like this, and I can push the submit button, and then it will appear here, and I can enter a new comment. So it's very simple, but it's hopefully suitable for showing the essential context, the essential concepts. So again, so for each comment, there's an author, and there's a text, and all these are part of the props object, which is communicated from the parent component. So here's another component class, which is the list of comments that you saw. So and you can see here that it instantiates the component that we saw in the previous slides, and it passes to it a JavaScript map which contains the author and the text fields that that comment is supposed to have. And again, you can see that this this component also receives arguments with the initial list of comments in the props object. So so again, this is JavaScript code that's translated straightforwardly into ClojureScript. So here we have an interactive component, which is the box at which is the thing at the bottom where you can enter a new comment, a new author, and a new text. And so you need two input fields here and here. And you can see that these input fields receive names. So even though this looks like it's regular HTML, it really is a feature of React. So these two DOM elements get names, and the form that those two input elements are part of gets a callback, and that callback, well, must be somewhere else. It's not on this slide. And indeed, you can define a callback when you create. So here's that. And so here's the callback that handles the events, which you can also which you also pass when you create the class for the component. And you can see, it calls some new comment thing that it also takes from the props with the author and the text of that new comment. So anyway, a couple details. So first of all, remember how I said that those two elements have names. Those two DOM elements, and these names then show up in an object called the refs, which the component receives, and that particular object we can then use to retrieve the actual DOM node, and from that actual DOM node we can retrieve the text that the user entered down here via the value field. Okay, so this is a little bit more involved. Is that reasonably clear? How it works, right? So you need to refer to the actual DOM elements, but you only have the virtual DOM elements from React, and this is the way to do it. So just to remind you, these were the two refs that were sitting there, and they correspond to the accesses to the refs here. Okay. So then component. So this was all fairly straightforward, right? As we saw that we had one component that just displayed a comment, and we had another component that would just be interactive and call a callback upon receiving a new comment. And in this case, so this is now the component that encompasses both of those. So it has both a comment list at the top, the list of comments, and it has the box for entering new comments at the bottom. And you can now see how these two things hang together, is that the new comment, this component, when it instantiates new comment, it will pass, remember how it called a method called new comment when there's a new comment? And it passes, well, something downward, and which is again defined as part of this particular component class. So here's that event handler. It will get called from the component below, and well, what it does is it obviously calls something called set state. So it will mutate the state of the component to include the new comment that's there. Okay. So well, first of all, notice that there's an imperative mutation operation here. Also notice that there's well, if you know JavaScript, you should, well, something in your spine should tingle, because there's some funny business going on with this. And so React takes great pains to managing this, this implicit parameter, and you then need to pick that up in ClojureScript to turn it into a lexical variable. So anyway, so with all this code, but what it really looks like is you have a tree of components that gets turned into a DOM tree. Each component instantiates the components below it and passes it properties or props. And each component can also manage some internal state up there and mutate it off an event handler. But what's really nice is that rendering is not part of this, right? React completely takes part of the rendering by having the component tree yield a DOM tree. And so the way it works is you might have, you know, here's your component tree. And then, you know, something happens, somebody pushes a button, and that leads to set state being called on several components. And of course, that means that these components are going to have to be re-rendered. If those components have to be re-rendered, their subcomponents have to be re-rendered. But remember, this is all acting on the virtual DOM. So this is just an object sitting somewhere. And it has nothing to do yet with the actual DOM that's being displayed in the browser. And so as a final step, React compares the virtual DOM it's generated with the DOM that's actually sitting in the browser, and then mutates the browser DOM so that it corresponds with the virtual DOM of your application. And that means that you don't have these funny cycles, and you don't have these consistency problems of the typically MVC application, where you have to wonder, well, if there's a particular change to my model, what is the corresponding change in the GUI? React completely conceptually recomputes your entire GUI, everything that's displayed, every single time there's a change, no matter where that change is. And that makes it really, really pleasant to deal with. So yeah, I felt I was getting closer to my original ideal of having something like the Racket teach packs work for GUIs. On the other hand, a whole bunch of details really bothered me about this. So first of all, there's still explicit mutation of state, right? And in particular, React imposes some structure on that state. It conflates application state with sort of transient GUI state. That's something the video games don't have. But if somebody types some text in your text field, you really don't want this in your application state until somebody presses return. Then you have to sprinkle all those hash.js around your ClojureScript code to generate JavaScript maps, which are not the same as ClojureScript maps. Then there's this funky handling of begin, of this. Then there's this funky handling of refs, where you need to stick a name inside an object in order to refer to it outside the object. And I wondered why you have one props object that you use to pass arguments, when usually you call functions and pass them named arguments. And so I wanted to fix those. On the other hand, you can get additional benefits by using ClojureScript together with React. For example, you can override a method called shouldComponentUpdate. And shouldComponentUpdate, well, is responsible for telling React whether something has changed. And we know, well, usually React doesn't know, and so it will always assume that something may have changed. It will re-render the DOM. It will compare it with the DOM in the browser. and synchronize the changes. But if you were able to tell it that nothing has changed without re-rendering, that'd be really nice. And of course, we're in the ClojureScript world where objects are usually immutable. And so if you make the assumption that things are immutable, we can just compare them and save React from having to re-render. And so we can make it even faster than React usually is. It is pretty fast. In particular, well, I'm sure most of you know that there's a really nice framework by David Nolan called Ohm, which takes advantage of precisely this. And it allows you to write React components in this style where, well, you can see that it looks pretty similar to the React formulation. Instead of those keywords that you use to identify the render method or the state manipulation, you use as protocols. And he has a special wrapper library for the DOM elements. But I mean, this part looks pretty similar, mostly to the original straightforwardly translated code, except that you can see that it does something with core async channels up there, right? So it does something. So we'll have to figure out what that is. And that has to do with callbacks. So in this case, this is some application for contacts, and there's a delete button somewhere. And instead of just calling directly a callback, when somebody pushes the delete button and then effecting the corresponding change in the model, what David did in the tutorial example is he sends a message to an Ohm channel, and upon creating the React component, he creates a core async go loop that will listen on that channel and will try to make the corresponding change. And so in this particular case, you can see, well, there's that go loop, receives a message called contact from the channel, and then it calls something ohm transact, which will remove that contact from the list, right? Well, so here's that transact thing. And it's got a bang there, so it's probably doing something imperative, right? And the corresponding contact view, which is sitting around it, will then just put a delete message on the channel when somebody pushes that button. Is that clear at all? Too complicated? Somebody shake your head if you don't, if it was like incomprehensible. Okay, we'll go on. If you don't interrupt me, I'm just going to go on. So, anyway, it looks a little nicer than the original React example. It still has hash.js sprinkled throughout the code, and it's got this thing that well, it's doing something imperative. It's not quite clear what it is from looking at the API example. And I played around with Ohm, and like the tutorial example, it says that if you write it naively, it says, you know, if you write this naively, there's immediately going to be a bug that you only see if you open the debugger window in the browser. And the reason is, well, you've got to make a change. Can you see what the change was? Can you see it? Well, it's there, right? And the reason is, even though kind of the program looks as though it gets past a contact that it's trying to display, it doesn't get past a contact, it gets past what's called a cursor. It gets called a reference to that contact in the larger app state. And you can only dereference that contact at certain times. And in this particular case, you want to the program tries to dereference it in the go loop asynchronously, and that happens to be a time when it's not available. So you need to dereference it beforehand. So you see state creeping in your development process suddenly. And on the first 1 or 2 hours of programming with Ohm, I immediately ran across this problem. So there's this concept of a cursor. You can read up on it. I found it pretty complicated, especially if the rules that say, well, when do you have a cursor? When is the cursor the same as the object that it refers to? I found pretty confusing. So also what it does, it creates a structural correspondence between your app state and your component hierarchy, right? So I mean, one thing Ohm does is it gives you a certain style of writing your programs where your entire application state is sitting in an entire in one object, and Ohm then the way Ohm is set up it wants your component hierarchy to correspond to the tree structure of your app state. And in many cases, that happens to work out just fine, but there's some cases where it doesn't work out, where your GUI is structured differently, and then it gets more difficult to do this with Ohm. So I wasn't very happy with it after playing around with it, because the internal state of the Ohm system leaks out, because you can't always dereference cursors when you want to. This transact operation, you can call it anywhere, and it will, even though it will just replace your app state object by another app state object, it's still an imperative operation that I wanted to keep under tighter control. And so that creates a pretty good, I mean, even though technically there's no mutable data structure, it's a pretty good mock-up of one, right? If you saw, if you saw this code, this transact thing, it sure looks like I'm setting the contacts field of the app state to this value, right? Which is not what's happening, but it's almost indistinguishable from that. So anyway, so cursors, the cursor API bothered me. On the other hand, you really need to think about how you're going to map parts of your app state to a single component. And that is something that we had to experiment quite a bit with when we designed our own framework. So here's what we came up with, trying to solve these gripes, trying to resolve these gripes that we had with React and Ohm, is something called Reacl that you can also download, I think even Google for, that I think is better. So you have a component hierarchy. As a component instantiates another component, you just pass it arguments that look just like arguments to a regular Clojure function. And you also, each component manages application state. In addition to managing application state, on the right-hand side, each component can also manage transient state, which is only something that people can see, but that you don't want to be part of your application state yet. So the question is then how to get that under control, and we got it under control by saying that every modification to the application state or the local state has to go through passing a message. So you need to reify each change into an object. I'll give you examples in a moment. That means you can't have uncontrolled manipulation of state, and also you can't manipulate state directly. Instead, you will have Reacl do it for you. And when there's a change to the application state, you sometimes want to communicate that upwards because it's part of a larger change in a surrounding application state, and that's when sending a message yields to what we call a reaction up above in the tree. So let me show you how it works. So here's a simple to-do application. So it's supposed to be this one. Yeah. Anyway, so there's already a to-do item here, right? Spend money, something like this. So it's really simple. You can check off items that you've already done, and you can delete items that you're no longer interested in. So it's really simple. And in this case, so we have an individual to-do item that has fields text and done, text that describes it, done that says whether it's checked off, and it also has an ID because you don't want to-do items that have the same words in them to be considered the same. Otherwise, you delete one and maybe you'd see the other one disappear. And then there's the application state, which just has a list of the to-do items and the ID of the next to-do that somebody might add. Okay. And so here's an individual item of that to-do list. And you can see that we have a custom def class form at the top. We have a parametered parent, which I'll talk about in a moment. And the application state is just the to-do object from that record definition that we saw on the previous slide. Now, one thing that we would like to do is, well, I'm getting ahead of myself a little bit, but you can see that there's an event handler here which wants to refer to the checkbox that you can check, right? Remember, in the original React, you needed to put a ref name into the object and then refer to that. And here we can use a form that looks just like let, called letDOM, which you can use to name individual DOM elements, and then you can refer to them in your event handlers. So that's like the first nice thing Reacl. So there's that. You can use letDOM to bind checkbox, and you can refer to checkbox to get the DOM node down here. Okay. Now you can see next that when somebody checks the checkbox or clicks on the checkbox, that leads to sending a message to this object. And so that really separates the modification of the state to describing the change or the action that happens in the GUI. And then actually handling the event is a separate thing that you do in a message handler that you also define, that you also put in the def class form. And here's the message handler for that individual to-do item. And and you can see, well, you can see that it receives a message called checked P. That is just whether that particular checkbox is checked or not. And you can see that it says, well, I want the new app state to be created from the original to-do item, and by replacing the done field by the value of the checkbox. Okay, and so this is really the heart of Reacl, is that message handler. It very much corresponds to those functions that you saw for the Racket teach packs. It's a pure function, right? And all the actual state manipulation happens by Reacl itself, and it means that there's nowhere in the program, there's no point in time where you can't access the data that you're interested in, for example. So this really is the heart of it, is that you can have pure functions define your event handlers. And you can also use this mechanism of sending messages, not just to send message to the particular component that you're in, but you can also use it to send messages, for example, to your parent component. So you remember there was a checkbox, and there was also a zap button, a delete button. And so what we do is we just send a delete message to the parent object. Okay, so far so good. Everybody nod. Okay, there's enough nods, thank you. A couple of thumbs ups, so somebody's still awake. So again, and notice that we also refer to the thing that we bound by letDOM up there. So we can use regular lexical binding that we've hopefully all come to love in Clojure to refer to our DOM elements. And so that's a single to-do item, and here's the application that's around it, the to-do app, and that will have both application state and local state. And the local state is responsible for handling the text that I've typed, right? You only want it to be part of the application state when I push the new to-do item button. And in this case, you can see that we call to-do item to instantiate a to-do item component, and it gets passed to-do, which is to-do item's parent, which is to-do item's application state. This is to-do item's parent, this. And also we pass it a reaction that says, well, if your application state changes, I really would like to know about it, and I want it to be turned into a message. And that message gets constructed by calling the change constructor of that record definition up there. So again, we just use the same mechanism as just to pass a message and then have the message handler be a pure function. So here's that reaction. So, and here's the actual event handling. So, for example, the submit button gets a regular event handler, and that event handler sends a submit message. And here's another event handler on changing the text of the text field, which just says, well, there's new text in the text field, and this is what it is. And you can see the corresponding record definitions up there. So there's that. And again, we have the message handler here, which now must distinguish, well, what is happening in my application. Remember, it could be either a new text record, a submit record, or a delete record. So we just look at it. We say, oh, okay, so somebody's typed new text into the text field for the next to-do item, and the text of the current to-do item is just sitting in local state. So we're going to use Reacl return to instruct our system that there's a new local state available. And now it's just very straightforward code, right? When there's a submit button, when somebody pushes the submit button, well, we want to clear. We want on the next iteration of the system, we want the text to be empty. That's up there, and then we just want to define what the new application state is, which is, well, we're going to take the old list of to-dos, we're going to create a new to-do item with the next ID number, with the text of the local state, which is the text, and it's not done yet. So it's a couple of lines of code, but it does something very straightforward. And of course, the next to-do item after that should have a higher number than this one. So, and then it gets really boring. But just so you see that it's the same thing, or somebody requested that an item be deleted, in which case we just, so by pushing the delete button that's right next to the item, in which case we just we just say, well, there's a new to-dos field in the application state, and it consists of all the elements with the one that we were looking for removed. Okay, and remember, there was a change message that could also be sent if somebody pushed clicked on the checkbox, and it's the same thing. We just go over all the items, look for the one that has the ID that is being changed, and replace it. So it's not anything particularly complicated. But I hope you can all see this principle involved here. Is that handling events is split into two parts, right? One of them is creating a representation of what is happening in your GUI, and the other one is and doing something with that, and the other one is actually saying, well, what is my application state going to be like after that GUI action? And that is a pure function. And so we feel that Reacl is doing a little better than if you just use plain vanilla React, and we also like it better than Ohm because it gives you lexical scoping. In particular, it gives you lexical scoping for DOM elements, and it does everything underneath to stick refs in and refer to them. You don't have any destructive manipulation of application state in your user code at all. There's no transact operator or anything like that. All message handlers are pure functions. We felt it was really a good guideline for developers to have them separate the app state, which is fundamental to your application, and transient GUI state, which is just something that the user sees, but which only maybe becomes part of the app state later on. We've been using it in production for quite a while now, but we're still making changes to it because sometimes we're discovering that we could make it better. So right now, I think the documentation is a little bit out of sync with reality, but hopefully we'll have that fixed in 1 or 2 weeks. But I'd be happy if somebody tried it out and gave us feedback. So there's that.
There may be a question or two.
I couldn't follow everything, actually. I don't know React in detail, and I don't know Ohm, but I understood your first slides about this video games and this fully functional world transformations, and like your last concepts and what are the pros and cons. But wouldn't be there a better solution, more looking like your first video game proposal? This looked like now a lot of code and then creating this DOM elements in ClojureScript and so on. So wouldn't be like the ideal solution be something what you showed first, where you have like a render and then less code and more.
Sorry, so that was the smallest example I could come up with that really demonstrates everything. So maybe that was a little bit too much. Let me first say that it is like World and show you the place that it is mostly like World, and maybe highlight the places where it isn't, right? So the main place where it isn't is this, right? Is in that we attach event handlers to DOM elements And those event handlers do something imperative, namely they send a message, right? This is the only place where it's not like the World Teach Pack. And arguably, we could make it be like that. Make those pure functions and then having the message machinery be in the background. On the other hand, it really would mean intercepting all the calls to the DOM construction, which we weren't ready to do yet, right? But if you remember, that picture that picture said, well, you need to translate the original picture of the Reacl system. I mean, the most important part. Sure, we'll get there. So that picture, right, really says, well, your event handler should be a function from your application state to your application state, right? So the event handler that learns so the event handler knows what the user has done, and then it just maps an application state, a world, to the next world, right? I'm sure PowerPoint professionals can do better at this, but you have to do with me. You have to make do with me. So, so this is just that same function, right? It learns what the user has done. The user has requested that the checked status of that particular to-do item be changed. You can't, and all it does is returns a new application state. I could have made it worse for you. I'm just saying, I mean, this is part of this, right? It's just sitting in those parentheses. And so, in particular, it refers to the old application state here. And that old application state is just coming from, I'm not tall enough, but you can see it there at the top. It was an argument to that thing. So I would say it's very close. The only place, really the only place is that we still let you attach vanilla JavaScript handlers to DOM elements, right? That's the only thing. And arguably, since I think most of our programs just say send message and nothing else, maybe we should just take the plunge. We just haven't been ready to do that yet.
Just two short questions. What do you think about JSX? If there will be any transform tool to transform from JSX to Reacl, which I found it very useful. So the other questions is what do you think about Flux, the application architecture which Facebook is promoting right now?
Excellent questions. So JSX, I should say, I didn't show you this, but JSX is sort of a preprocessor for JavaScript programs. That's also part of React that allows you to write HTML templates in your code. I think that's fine, but we don't have anybody who really is able to do anything better with that. I think that HTML notation is mainly useful for designers who know HTML but who don't want to do JavaScript, and we just don't have any in our organization. It might be that in some future collaboration with a designer, somebody tells us, well, if I could only write HTML syntax, then we would do that. And I don't think it would be a big deal. I don't know how to make ClojureScript do this with reader macros or something. But actually, Reacl has something very similar that lets you write XML syntax. The other question was the Flux application architecture. I mean, the thing is, it's sort of a pattern, right? And we're functional programmers. Most patterns are supposed to be code, right? If you look at this, it really codifies something that's, offhand, I couldn't tell you the difference between this and the Flux application architecture. I think it also encourages you to make that separation, to really give that, to really define those transformations in a very, very similar way. It's just that here we have the means to codify that into an interface, right? And so I think it's fine. I think there's still some bits missing that we do that Flux isn't quite clear on. But I think ultimately what we're doing is we're just realizing Flux as an API instead of as a bunch of videos. which is what Facebook is doing.
Hi.
Hi.
I just had a question about the message handler.
Yeah.
And the way I understand it, any message handler in any component is still allowed to manipulate both global app state and local app state. And I was just thinking, when you're using this in production, do you tend to put most of the global app state manipulators in one place, or how do you organize that and still kind of stay sane where the changes to global app state comes from?
Yeah. Very good question. So so the answer is, and I probably didn't explain this very well, is each component has its own app state and local state. Okay. So each component. So when you see this, right, this app state thing, it really refers only to. We call it app state. And you might conceivably have an app state that's shared among components, but is really associated with that component. And your top-level component is typically going to have the state of your entire application. This reaction mechanism that I showed you, right, coordinates between the app state of the subcomponents and the parent components. This is a very good question, because until a couple of weeks ago, I mean, I'd already submitted this talk, is we really had a global app state, and we had a system of lenses to manipulate that global app state modularly among the components. But we then switched to this, and it really allows you to explicitly say, well, it allows you to isolate the subcomponents from the supercomponents, because all the subcomponent can do when something's changed, it can send a message upwards, and there has to be a corresponding message handler that knows what to do with it. If it's not there, then you have that makes it for a clearly defined interface. Does that answer your question? Okay, thanks.
Okay, so thank you very much once again.